Everybody okay? Alright, so shall we proceed to more information about short channel characteristics? So far, you already learned on long channel, right? Long channel. And this is the most interesting part we call a short channel, because short channel is the demand nowadays. This is normally applied in the site design. Short channel, one for NMOS, another one for PMOS. Of course, we must know both first before we look at the CMOS part. Okay, for short channel, normally whenever the transistor length is less than 0.25. Nowadays we have 45 nanometer, 32 nanometer, but for this training, we want all the participants to know the behavior, okay, on how to do the circuit analysis. Then that's why we are using greater than 32 nanometer, 0.25 micrometer. So it started from this point where the threshold voltage appearing at this point, and then it will slowly increase. Normally the threshold voltage is somewhere at 0.43 because this is a VDS. Okay, VGS at 0.43, and what we see here is the drain source voltage. Okay, the effect of VDS to current. As I mentioned, current is normally depend on IV characteristic, on VGS and VDS value. It normally depends on VGS and VDS value. So the current equation is useful, okay, to as a means the MOSFET, whether NMOS and PMOS, is working in linear regions, saturation region, and at some point it will be in velocity saturations. Why velocity saturations is important in short channel? Why? Because the size is shrinking. Okay, so another effect. Okay, another effect called velocity saturation, and you will get the current less than the saturation region. This is how it looks like. So you can see long channel, it will get greater current, but short channel, smaller currents with similar gate source voltage. So this is important because we want to reduce power consumptions. Okay, so the currents and voltage, smaller voltage will give you smaller power. Okay, velocity saturation causes a short channel device to saturate at smaller value of VDS. So drop in current. How about PMOS? Just now we look at NMOS, right? So here is about PMOS. In PMOS, in reverse direction. Why reverse direction? Why reverse direction? As you already learned during this training, the symbol itself of PMOS is different compared to NMOS. The directions, this one for NMOS, and this one for PMOS. Here is the gate, source, drain for NMOS, and meanwhile for PMOS, gate, drain, source, reverse. So the current flow this way, drain to source, and meanwhile current flow for PMOS in these directions. What we can call this one in reverse positions, in reverse order of NMOS. That's why we can use NMOS and PMOS as inverter. It's complement each other. So the directions in terms of plotted graph, we can see where we apply in negative value to PMOS, then you will get the currents in this direction as well. Okay, so reverse order of NMOS operations. So normally, engineer will use this unified MOS current model to determine the operations of MOSFET, whether it's working in linear region, saturation region, or velocity saturation. So this is the parameter extracted from SPICE model. When you're working as engineer, when you come to the design, you will need the data sheet. They will give you a PDK data sheet, includes the MOSFET's parameters, SPICE model, and what I extracted here is only 5 parameters. Okay, because we want to use the first equation. Okay, the first equation of MOSFET, unified MOSFET. So the most important equation is this one. We use this one by understanding VGS minus VT greater than 0, which is VGS greater than VT. VGS must greater than VT. I will put modular signs. Okay, normally we will consider modular sign because we have PMOS which is working in reverse order. But this is the equation, but you must understand it very well. The directions, then you will get apply modulus symbol there. Okay, how to estimate, how to define whether the given MOSFET is working in 3 different modes. So if MOSFET has the smaller value VGS minus VT compared to these two, then it's working in saturation region, pinch off saturation, like we can call pinch off saturation. So there is 3 modes. Okay, pinch off and velocity saturation. Okay, this is very important to determine before we do the current calculation. Okay, before we do the current calculation, we need to estimate what is the value occurs in minimum value. Let's say if you're thinking about pinch off saturations, it's supposedly VGS minus VT smaller than VDS saturation, smaller than VDS value. If we are looking at velocity saturations, then VDS saturations is smaller than VGS minus VT, smaller than VDS. Okay, how about linear region? Okay, you learn about linear region earlier, right? During this training. Linear regions, whenever VDS is the smaller value, okay, smallest value compared to VGS minus VT, and I can call VDS saturations and VGS minus VT. So if you look these directions of information, then you know the current should be working in pinch off, velocity, or linear region. Okay, then you can estimate the current value. So let's look more information about that. Okay, this is the equation. Now we have this information on how you can figure out on how to use the equation. Let's say we're still using this lambda VDS. You can ignore this value. If you ignore this value, it's only this equation. Okay, look, this is for long channel. Okay, for long channel or for short channel, normally we exclude lambda VDS. Okay, we exclude lambda Vs. So at velocity saturations, we will replace this VDS. Look at this equation, V minimum. Okay, this is V minimum, V minimum. So substitute V minimum here. If you are looking at in linear region, so this is the V minimum. You replace or substitute the equation with VDS. Okay, also with this one. And if when we calculate what is the minimum voltage, it's working in saturation voltage, VDS saturations, then we substitute V min with VDS saturations together with this one as well, because this is a part of the equation. Okay, so this is in very general. So how about PMOS? PMOS is the reverse order of NMOS operation. Okay, we come to the second part of these informations, where you can see if VGS smaller than VT, of course there's no current flow. That one in cut-off region. Okay, everybody know that. Okay, can you notice the behavior of MOSFET as switch? When it's turned off, ID is 0. When it's turned on, it in saturation region, right? Okay, so saturation region, whether in two conditions. What are the two conditions, Miss Christina, for saturation? What are the two conditions for saturation? We have two kinds of saturation region, right? One called pinch off, one called velocity saturation. Okay, great. Okay, so let's do one more activity. Okay, consider an N-channel MOSFET with a threshold voltage. Remember threshold voltage? Play the main role here. But I give you 2 volt. Analyze the device switching characteristics by obtaining the drain current. You want to get the drain current, okay? As a function of gate voltage equal to 2 volt and 4 volt. So you have two kind of calculation. One for 2 volt and another one for 4 volt. For the following regions: linear region, saturation region, pinch off conditions. Okay, I want you to share, to work with other participants, everybody to work together. And can you just write down your answer on paper or on iPad or tablet or any mediums? Okay, then you screenshot your answer and put it in Padlet. Can you? Okay, you can scroll to, can get access to this Padlet. Okay, I think it's given in my handout for training today. The second activity. Okay, can you get access, Dr. Nusrat?
Yes.
If you don't think you can access Padlet, then you can write your answer here. So shall we check Padlet? Okay, everybody can put your answer. This is given scenarios. Okay, one more thing. Let's assume the transconductance, is equal to 200 microwatt. Okay, let's assume the transconductance, I write more here. Let's assume transconductance equal to 200 microwatts per A squared. Please remember you need to consider linear regions and saturation regions. For two different voltages, one for forward, another one for toward. to put your answer in Padlet so we can discuss?
Doctor, we find out the equation for ID only, or we need to calculate the exact answer.
Okay, you need to upload on the final answer.
Or I need to calculate the exact value.
No need to calculate the exact value. We want you to check whether it's confirmed in linear regions, where you have to consider linear region operations and saturation operations. So it looks like you have two calculations for that. Okay. So of course, when you have a voltage at 4 volt, okay, 4 volt. So remember that is the VGS, right? VGS equal to 4 volt. So VTH is equal to 2 volt. So you don't to be exact value of current, because for these informations, you not given the you also been given VD. Let's say, assume your VDS at also at 2 volt. Let's assume VDS at 2 volt. You can also assume VDS at 2 volt for all conditions. Since in linear region, you need to know what is VDS value. Okay. For saturation regions, can you strictly use that value given here? VGS equal to 2 and 4. Okay. You just can drop the final answer only. Okay, you don't need to screenshots your answer. Just give me the final answer. Let's see, can you manage to utilize the given equations to get the current value for this condition, these two conditions? No need to consider VDS saturation. Okay, only pinch of saturation. Okay, how about you, Miss Nabila? Okay, can you share your answer in Padlet? Don't worry of making mistake. This is the training where you sign up to know how to do it, right? Okay, we have one answer here. ID, whenever it's working in linear regions, ID equal to 0 ampere. Okay, VGS is equal to 2. VGS is equal to 2. Then minus 2. Okay, of course you have the equation Kn. How about the width over length? We think width over length is equal to 1, yeah? Width over length, if we assume width over length is always at 1, okay? So the answer mentioning at this point, so let me write, so you have ID equal to 0, saturation equal to 0. For VGS equal to 4, ID is equal to 300 microampere. And the second ID is 400 microampere. I would say the second part is correct for the saturation region. For the first part with linear regions, okay, for the linear regions, so you assume will be 400 microampere, right? 400 microampere, this is correct. So supposedly when it comes to 4 volt, both in 400 microampere. Okay, so after this training, maybe you can see my handout. I will share with everybody the solution for this activity. Okay, so what I want you to why I asking you to do this analysis, so hopefully you know where about to use the equation for linear region and saturation region. Now I think everybody know how to use it. Okay, maybe when you get a more small channel length PDK, then you can apply the similar calculations analysis for that. Okay, right. So I give you some time. Maybe after this training, you can still upload your answer in Tablet, because you see during the course overview, I mentioned about the in class or in training activity. You will be will be evaluate. I will evaluate you in terms of the competency. Okay, we want to see your competency for this training. Okay, shall we proceed to see what you have encountered so far? You'll be able to model the switching. You'll be able to model the switching, and it looks like you are seeing the current conducting on resistor, because MOSFET is look like a resistor. When it's turned on, when it's turned off, it's like open switch. So it all depends on the width over length. Okay, so that's why I'm using width over length equal to 1. Okay, equal to 1 for the example and as activity. Alright, we still apply the same SPICE model of 0.25 micrometer for this training. Maybe when you look at another parameters, let's say in your working path, you will see different parameters of this resistor and transistor. Now, MOSFET also have capacitance. This capacitance is important because you will need to do the RC analysis. It includes the capacitance and diffusion capacitance. This is the source of capacitance, where this is about the CMOS inverter. Okay, CMOS inverter, in this training, you will go further analysis of capacitance. Before we look at more detail on capacitance, look on this architecture of CMOS inverter. It consists of PMOS and NMOS, and this called cascaded. Because when you have a large and complex design, you will need to cascade the design. Okay, what do you think about a ring oscillator? Ring oscillator.
I don't have idea.
Okay, ring oscillator also use the cascaded method. Okay, however, it's like a loop back to the first input. So can you imagine people working in signal processing using something like inverter to get the signal? Okay, so this is another application. Right, from a very simple constructions of MOSFET, PMOS and NMOS, create a simple inverter, and then that can be used to tune the frequency. Okay, so we have two types, intrinsic and extrinsic capacitance, and this is used to fan out, and this one for intrinsic capacitance. Okay, we will look at more details on inverter design, but I hope that you will really understand the behavior of PMOS and NMOS, and we can use that for the rest of the training of CMOS inverter in this training. Okay, let's complete your your analysis for the given activity. I give you like 2 minutes to complete that. Then we can continue with another a module for this training. Okay.